Alright, so we're going to begin working through test number 4 here on circular motion and universal gravitation. So we'll start with this first conceptual question. We have this hammer being spun around in a circle like that, and we first want to know the direction of the acceleration at the moment shown. So that acceleration is going to be going directly to the left like that. And our reasoning there is that whenever we have an object traveling in a circle, the acceleration is always inward towards the center of the circle. Next question asks, if the object is released at this moment shown, which target here, A, B, or C, are we most likely to hit? The key here is that the velocity is going to be tangent to the circle, so that blue line shows the direction of the velocity, which means once it's released, it's just going to travel in a straight line. We no longer have that inward force to make it accelerate. So it will travel in whatever direction it was traveling in. In this case, that direction tangent to the circle will cause it to go directly up and hit target B. All right, moving on to this next one here, we have a person going around a circular track. We want to know what speed the person is riding around the track. And so we're going to start, of course, with our free body diagram. This is one of those horizontal circles, so we're going to do that side view that we often do when we have a horizontal circle like that. And in that, we have the force of gravity going down, we have the normal force going up, and then the force that keeps us moving in a circle is that force of friction. And that, of course, is causing our inward acceleration here, that acceleration towards the center. Now that we have that, we're going to go ahead and set up our max and may. I'm going to start with my may here. So in the y direction, we have our normal force going up minus our force of gravity going down, and that's going to be equal to 0 in this case. We're not accelerating vertically here. We can, of course, plug in mg for our force of gravity. That mg is going to be 95, our mass, times 9.8. And when we solve for our normal force, we find that it's going to be equal to 931 newtons. Now that we have that, I'm going to go ahead and set up my max. So in the x direction, the only force I have here is going to be that force of friction. That's going to be equal to 95 times my acceleration. We do have one in the x direction because we're traveling in a circle. For friction, of course, I can sub in mu times my normal force, so that equals 95a. Coefficient of friction is this 0.68 from up here. I just found my normal force was 931. So that equals 95a, and what I end up getting is 633 equals 95a. So my acceleration then is going to be equal to 6.66 meters per second squared. From there, I can go ahead and ultimately solve for the velocity, and I'm going to do that using the fact that that acceleration is just v squared over r. So 6.66 is equal to v squared over 20. I end up getting then that v squared, when I multiply by 20, is 133. And so my velocity, taking the square root, both sides, ends up being 11.5 meters per second. With that, I can then go ahead and figure out how long it will take to complete one full lap of the track. What I'm thinking about now is trying to find the period of that motion around the track and linking that to the velocity. And so I'm going to use v equals 2 pi r over t. So this velocity here, 11.5, is going to be equal to 2 times pi times my radius, which is 20, all over that period, which is what I'm trying to find. Multiplying that top out, I get that 11.5 is going to be equal to 125.6 over t. From here, I can put that over 1 and cross multiply, and I get 11.5 t equals 125.6. So my period then, that time for one lap, is going to be 10.9 seconds. Alright, so for this question, we once again have an object moving in a circle, or at least part of a circle, but either way, we're going to set up the forces acting on that object while it is moving in a circle. So this child, of course, is going to have the force of tension from the chain there, going up, and we're going to have the force of gravity going down. We, of course, are accelerating upwards towards the center of the circle. So I'm going to go ahead and set up my F equals ma. Here, I only need one in the y direction because it's a vertical circle, and there are no x forces. So it's just going to be Ft minus Fg equals may. So I can say my force of tension minus mg is going to be equal to may. So the force of tension minus 30 times 9.8 is going to be equal to 30 times my acceleration. I don't know that, but I can find it. I know that whenever I'm traveling in a circle, my acceleration is going to be equal to v squared over r. And I'm told here that at the bottom, the velocity is 3.5. The radius, which is the length of this chain here, going to the center of the circle, is 1.8. And so I get an acceleration here of 6.8 meters per second squared. So I can go ahead and substitute that acceleration in to the equation here. So what I end up getting is Ft minus 294 is equal to 204. Solving for Ft, I find that that tension is equal to 498 newtons. Second part of the question asks what happens if the child goes up and over. We want to know what is the minimum speed the child must have to not fall off at the top. Okay, so when we're at the top, we of course have the force of gravity going down. If we're in that case though, when we're at that minimum speed, okay, and we're accelerating down, there actually is no tension force. We're going as slow as possible. If we went any slower, this child actually would go up and fall out of the circle or off the swing. So there is no tension. There's going to be slack in the chain, rope, whatever, when we're at the top. All right, and that's what that piece means. That minimum speed means we're not going to have that tension force at the top of the loop. So knowing that, we can set up our F equals ma once again, but the only force we're going to have is the force of gravity going down. Because both gravity and the acceleration are down, I'm just going to make both of them positive. I can then substitute in that force of gravity that I got before up here, which was that 294. So 294 equals 30a, which means my acceleration is 9.8 meters per second squared. And that makes sense because gravity is the only force acting on it. It should be in free fall, accelerating at 9.8 meters per second squared. Once we have that, we can use that acceleration now to solve for our velocity. It's no longer 3.5, but we can find it using a equals v squared over r. We multiply by 1.8 there, and so we get 17.64 equals v squared, which means when I take the square root, my velocity is 4.2 meters per second. All right, for this next one, we're worried about this satellite here that's orbiting Venus. So there's Venus. We're told the height of the satellite above the surface is this 3 times 10 to the 5th meters. And we want to know what is the gravitational force that Venus exerts on this satellite. So keep in mind the distance we really care about is the distance from the center of the planet to that satellite. And then we're just going to use our Fg equation. Fg equals gm1 m2 over r squared. And we're going to use that to solve for that force of gravity. So we go ahead and set that up. We know that g, of course, is 6.67 times 10 to the negative 11th. The one mass we're going to have is the mass of the satellite, which is 3,500. The other mass we're going to have is the mass of Venus itself. And to get that, we're going to look up our planetary data, and we see that it's 4.87 times 10 to the 24th kilograms. And that's going to be all over our radius. Now keep in mind, we have to do that radius from the center of Venus. And so what that ends up being is we're going to take the radius of Venus itself, which again we get from our planetary data sheet, 6.05 times 10 to the 6th, and we're going to add in the height above the planet, and then we're going to square that. Alright, so at this point it's just a matter of entering this into our calculators. I am going to break this down a little bit though, so If we multiply out that top part, we end up getting 1.136 times 10 to the 18th. And then on the bottom, when we add those two distances, the radius plus that height above the planet, ends up being 6.35 times 10 to the 6th squared. Okay, and so we end up getting FG is going to be 1.136 times 10 to the 18th all over 4.03 times 10 to the 13th. And when we do that in our calculator, we end up getting an answer here of 28,200 newtons. So that's going to be our force of gravity. All right, for this problem here, we have these two dwarf planets. So we know on the one dwarf planet, Makemake, the acceleration due to gravity is 0.6 meters per second squared. And we want to figure it out on this other planet, Eris. And we know stuff about the mass and the radius of Eris. So what we're going to do is we're going to go ahead and each time we're going to be thinking about our equation for the acceleration due to gravity, which is gm over r squared. And so I'm going to set up that equation for Makemake and for Eris. So we'll start with Makemake, and for that planet, we can say 0.6. That's the value of our acceleration due to gravity. We don't know the mass or the radius, so I'm just going to leave them as m and r squared. I'm now going to do the exact same setup here for Eris. And so it's going to be g, because that's what we're ultimately looking for, the acceleration due to gravity on that planet, is equal to g times the mass is 5 times as much, so I'm going to say this is 5m. The radius is twice as much, so I'm going to say it's 2r. Just be careful, we need to square that entire quantity. And so we end up getting g is equal to g times 5m all over 4r squared. I'm going to go ahead and pull out those constants there, 5 and 4. And so really it's 5/4 times gm over r squared. So I just rearrange that equation, taking this 4 and moving it out, and that 5 and moving it out in front. And what we end up seeing here is that this gm over r squared is the same as here. And so that really has a value of 0.6, so we can say g on this new dwarf planet, Eris, is 5/4 times 0.6 times the old acceleration on Makemake. So it ends up being 0.75 meters per second squared. All right, for this next one, we have two moons orbiting in this diagram, Moon A and Moon B orbiting some planet. We're asked two conceptual questions about this. So to start, we want to know which moon will take longer to orbit the planet one time. And really for this, we're drawing upon Kepler's third law, which tells us that objects that are further away from whatever they're orbiting, planets, moons, whatever, take longer to orbit. So because B is further away, has a bigger orbital path, B must take longer to orbit, and that really comes from Kepler's third law. For B, we want to mark the location on B's orbit when it's traveling the slowest. So for this one, we're thinking about Kepler's second law, which is the planets sweep out equal areas in equal time, but really what that means is planets are traveling the slowest when they are the furthest away. So right here is going to be the slowest speed for Moon B, and the reason is it's the furthest away from the planet here at that point. Okay, so it's going to be traveling the slowest at that point. All right, so for this problem, we're concerned with the orbit of Rhea, Saturn's largest moon. The first thing we're asked to do is figure out what is the average distance between Saturn and Rhea based off of some things we know about Rhea, one of them being the orbital period. And so what I'm going to use is I'm going to use Kepler's third law, and I'm going to use this form of it, the 4 pi squared r cubed over gm, and ultimately I'm going to be looking for this r value. That is the average distance between Saturn and Rhea. With this equation, though, that t, the period, needs to be in units of seconds. So I need to start with 4.52 days and convert days into seconds. So I'll go 1 day is 24 hours. I know that 1 hour is 60 minutes, and 1 minute is going to be 60 seconds. And so that ultimately allows me to go from days into units of seconds. And when I do that, I end up getting a period of 390,528 seconds. So that's what I'm going to end up using as my period in this equation. Okay, so I'm going to go ahead and plug in the things I know here. So this is going to be 390,528 squared, because the period squared, is equal to 4 pi squared times r cubed. That r is what I'm looking for, all over g, which is 6.67 times 10 to the negative 11th, times m. And the m I want here is not the mass of Rhea, but the mass of the central object, which in this case is Saturn. So I'm going to use, for that m, 5.69 times 10 to the 26th, which is the mass of Saturn, the thing it's orbiting. I'm going to show the next step here. So when I square that period, I end up getting 1.52 times 10 to the 11th, and that's going to be equal to 4 pi squared r cubed all over. And when I multiply those things together on the bottom there, I get 3.79 times 10 to the 16th. I'm going to go ahead and cross multiply here, putting this over 1. And so I end up getting 5.77 or 5.79 times 10 to the 27th is equal to 39.47 r cubed. So that means when I divide by that 39.47, I get 1.466 times 10 to the 26th equals r cubed. I'm going to take the cube root of both sides, and I find that r is going to be 5.27 times 10 to the 8th. The units here would be meters. All right, so that's how far, on average, Rhea is from Saturn. For the next part, I want to know the orbital velocity. So I'm going to use my equation for the velocity of an object traveling in a circle. Now, it may not be a perfectly circular orbit, but it's going to be close enough, and we'll just ultimately find the average velocity. So for this, I'm going to use the radius of the orbit, which is the number that I just found, that 5.27 times 10 to the 8th. And I'm going to divide it by my time, the period, but I want to keep it in seconds, so I'm going to use the 390,528. And the reason I'm doing that is that's going to give me my velocity in meters per second. So when I do that in my calculator, I end up getting an answer here of 8,484 meters per second. So that's the velocity of this moon as it's in orbit around Saturn. The last thing I'm asked to find is what is the acceleration due to gravity on the surface of the planet. All right, and so for that, when I'm thinking about acceleration due to gravity, I'm going to be thinking about G equals gm over r squared. That's what that acceleration due to gravity is. I'm now using things exclusively about Rhea. We're on the surface of Rhea. All right, so here is Rhea. There's an object, person, or whatever standing on the surface. So what we really care about are the dimensions of Rhea. So I'm, of course, going to plug in 6.67 times 10 to the negative 11th for g. The mass I'm going to use is the mass of Rhea, which is up in the data table above. All right, that's going to be the 2.31 times 10 to the 21st kilograms. And then the radius is going to be not the radius of the orbit, because we're on the surface, but the radius of the moon, Rhea itself, 1.53 times 10 to the 6th, and that's going to be squared. And so I end up getting that g, in this case, is going to be 0.066 meters per second squared. So pretty low, but it's a relatively small moon, so that's not that surprising. All right, for the last problem here, we're given information about two stars or a star, and two planets that are orbiting it, planet A and planet B. We know some stuff about planet A. We want to figure out the orbital period of planet B. This is a great candidate for doing this form of Kepler's third law, TA squared over RA cubed equals TB squared over RB cubed, because this allows us to compare two things orbiting the same object. In this case, these two planets orbiting this distant star. So we know that planet A has an orbital period of 45 years, so I'm going to put in 45 for TA. It does need to be squared. We don't have to convert here because with this equation, as long as we're consistent with our units, it doesn't actually matter what those units are. We don't know the period for B, so I'm going to leave that as TB. What we do know, though, is we do know something about the radius of orbit. Now, we don't know the exact numbers, but we are told that planet A is twice as far away as planet B. So for planet B, I'm just going to say the radius is R, and for planet A, I'm going to say it's 2R. We do need to cube those, though, because that's what our equation has. So I'm going to go ahead and take this equation up here. What I end up getting is that 45 squared gives me 2,025 all over 8r cubed. And the reason is we have to cube both the r and the 2. Okay, you can't just cube the r. And that's going to be equal to tb squared over r cubed. At this point, I'm going to go ahead and cross multiply. And so we end up getting 2,025 r cubed equals 8r cubed times tb squared. We see there's an r cubed on both sides, and so it goes away. And I end up getting that 2,025 equals 8tb squared. So we'll divide by 8, and I get 253.1 equals tb squared, which means the period is going to be 15.9, and the units will be years because that was the units I used for my original period that I plugged in over there.